Scientists in China just switched on a computer chip that is only 3 atoms thick. That is not a typo. 3 atoms. Think about how small an atom really is. You cannot see one, not even with the strongest microscope in your school. Millions of atoms could fit inside a single grain of sand. Now stack just 3 of them on top of each other. That stack is thinner than smoke, thinner than a soap bubble, thinner than almost anything you have ever touched with your own hands. And yet, this paper-thin sliver of material can do real math. It can move data from one place to another. It can run actual computer code, the same basic kind of code that runs inside your phone or your game console. Nobody thought something like this was possible outside of a movie about the future, but it just happened, inside a lab in Shanghai, and it might change how every computer on the planet gets built one day. Here is the strange part. This tiny chip is not fast. It is almost 1,000,000 times slower than the chip inside your phone. It has less raw power than a cheap calculator from decades ago. Here is a number that puts things in perspective. The chip inside a modern phone packs in tens of billions of these tiny switches. This new experimental chip only has about 5,900. That sounds like a huge letdown. Until you learn that just a few years ago, nobody on Earth had ever managed to connect more than about 100 of these particular switches together, no matter how hard they tried. Going from 100 to nearly 6,000, using a material this thin, is the part that has scientists genuinely shaken. So why are engineers all over the world calling this one of the biggest chip breakthroughs in years? The answer is not about speed at all. It is about something much bigger. It is about proving that a totally new kind of computer chip can actually be built in real life, not just imagined on paper. And once you understand how a team of scientists pulled this off, you will see why this tiny, slow chip might be the first sign of huge changes coming to every computer on Earth. Before we get into that, if you like learning how tomorrow's technology gets built today, hit subscribe. We dig into breakthroughs exactly like this one and explain them in plain, simple words, long before they ever show up in the regular news. No science degree needed, no confusing terms, just the real story, explained clearly. So go ahead and click subscribe now, so you do not miss the next one. Now, to really understand why this chip is such a big deal, we need to go back and look at a problem that has been quietly building for years. A problem hiding inside every single phone, laptop, and computer you have ever owned. Silicon hit a wall. For more than 50 years, almost every computer on Earth has followed one simple plan. Take the tiny switches inside a chip, make them smaller, and pack more of them together. Smaller switches use less power. They also work faster. That one simple trick is the entire reason computers went from filling up whole rooms to fitting comfortably inside your pocket. These tiny switches are called transistors. Think of a transistor like a light switch, except instead of turning a lamp on or off, it turns a tiny bit of electricity on or off. A single modern chip can hold billions of these tiny switches, all flipping on and off billions of times every single second. That non-stop flipping is what lets your phone play a video, load a game, or send a text in the blink of an eye. For decades, the plan was simple. Just make the switches smaller. Smaller switches meant more of them could fit into the same tiny space. Chip makers got incredibly good at this game. Every couple of years, they found a way to shrink things down even further, and computers kept getting faster and cheaper at the same time. But there is a limit to how small something can get before it stops working the way it is supposed to. The material used to build almost every transistor on Earth is called silicon. Silicon is cheap, it is easy to shape, and it has powered the entire computer industry since the very beginning. But silicon has a hidden problem. When engineers try to make a silicon switch too thin, it starts to break down in strange ways. Picture a garden hose. A thick, sturdy hose controls water really well. You twist the valve, and the water stops completely. But now imagine trying to make that same hose thinner and thinner, over and over again. At some point, it would start to leak, even when you were sure you had shut it off all the way. That is roughly what starts happening inside a silicon transistor once it gets too small. Tiny bits of electricity begin to leak through. Even when the switch is supposed to be completely off, the chip wastes power. It heats up, and the clean, sharp difference between on and off starts to blur into a messy gray area. There is a second problem too, and you have actually felt it yourself. Every time your phone or laptop gets warm after heavy use, that heat is coming from billions of these tiny switches leaking a little bit of wasted energy. Now imagine packing even more switches into that same tiny space, all leaking just a little bit more each. The chip starts acting less like a calculator and more like a tiny frying pan. Engineers have to slow things down, add cooling, or find other tricks just to keep the whole thing from overheating. Engineers have found clever tricks to delay both of these problems for years. They have folded the switches into taller, more complicated shapes to squeeze out a little extra control over that leaking electricity. Those tricks worked for a while, and honestly, they were impressive feats of engineering. But even those clever shapes are starting to run out of room. Silicon, as a material, simply was not built to get much thinner than it already is. There is an old story that helps explain why shrinking something over and over eventually becomes impossible. Imagine placing a single grain of rice on the first square of a chessboard, then 2 grains on the next square, then 4, then 8, doubling the amount every single time you move to a new square. By the time you reach the very last square on the board, the total number of grains would be so massive that it would outweigh every grain of rice ever grown on Earth. Chipmaking followed a strangely similar doubling pattern for decades, roughly doubling the number of transistors packed onto a chip every couple of years. People even gave that pattern a name, Moore's Law, after the man who first noticed it. For a long time, that steady doubling felt almost magical, like it might just continue forever. But just like the rice on the chessboard, a pattern like that cannot keep going forever in the real world. Eventually, you slam into a wall. Silicon hit that wall first. So scientists around the world have spent the last couple of decades hunting for something new, something that could work as well as silicon, or maybe even better, at sizes silicon could never dream of reaching. That hunt eventually led one team of researchers in China to a strange, incredibly thin, and almost magical material. To understand how something this thin can even function as a real computer chip, we need to zoom in even closer and look at the material itself, thinner than smoke. The material at the center of this whole story has a big scientific name, molybdenum disulfide. That is a mouthful, so for the rest of this video, we will just call it moly. Moly is made from 2 simple ingredients, a metal called molybdenum and an element called sulfur. When you arrange them in a very specific pattern, they form a sheet just 1 single layer thick. 1 layer of molybdenum sits sandwiched between 2 layers of sulfur, kind of like the meat between 2 slices of bread. That whole sandwich adds up to just 3 atoms deep, from top to bottom. Here is a way to really picture how thin that is. Imagine blowing up a single strand of your own hair until it was as wide as an entire football field. Even at that massive size, this material would still be thinner than a sheet of paper lying flat on that field. It is almost impossible to imagine something that thin actually doing any useful work at all, let alone running a computer program. Scientists had actually tried a different super thin material before this one, called graphene. You may have heard of it. Graphene is famous because it is incredibly strong for its size, and it lets electricity race through it almost effortlessly. For years, plenty of researchers hoped graphene would become the answer to replacing silicon completely. But graphene has one big flaw that kept tripping people up. It conducts electricity so easily that it is nearly impossible to switch it completely off. Remember, a transistor needs to snap cleanly between on and off, just like a light switch on your wall. Graphene behaves more like a light switch that is always just a little bit on, no matter how hard you try to flip it off. That makes it a poor match for building the kind of sharp, reliable switches a computer actually needs to function. This is exactly where moly has a real advantage over graphene. Unlike graphene, moly can be switched off almost completely, much like silicon can. Except moly is thousands of times thinner than silicon. And strangely enough, being that thin actually helps control the flow of electricity even better, because there is barely any material there for stray electricity to sneak through or misbehave inside. There is another quiet advantage hiding inside moly's thinness too. Because the material is only 3 atoms deep, the tiny control switch sitting on top of it has an almost perfect grip on every single atom inside the channel below. Picture trying to steer a toy boat across a puddle versus steering a real boat across the ocean. The thinner and smaller the puddle, the easier it becomes to control exactly where that boat goes. A thicker material gives electricity more room to wander off and misbehave. An impossibly thin one barely gives it anywhere to hide. On paper, this sounds like the perfect answer. Build transistors out of moly, make them incredibly thin, And maybe you can keep shrinking computer chips long after silicon has completely hit its wall. But here is the catch that stopped every research team before this one. Making a single, perfect moly transistor inside a lab is one thing. A researcher can hand-pick the cleanest, most perfect little spot on a tiny sample and get beautiful results every time. But a real computer chip does not need just one perfect transistor sitting by itself. It needs thousands of them, or millions, or eventually billions, all working together, all behaving the exact same way, at the exact same moment, without a single one falling out of line. Before this new breakthrough, the actual world record for connecting these moly switches together stood at just 115 transistors, set years earlier by a different research team working in Austria. That number had stood untouched for a long time, almost like an unbroken sports record that nobody could beat. It is nowhere close to enough to build anything that could honestly be called a real working computer processor. It was more like proving you could balance one domino upright, when what you actually needed was to line up thousands of them in a long chain and have every single one fall exactly the way you planned, without a single domino getting stuck or falling the wrong way. There was also the question of what to even build these fragile switches on top of. You cannot just lay atom-thin material down on any old surface. The researchers needed a base that would not interfere with the tiny electric signals flowing through their switches. Something almost like a perfectly smooth, silent table. They chose sapphire, the same tough, clear crystal used in fancy watch faces and bulletproof glass. A thin, round sapphire wafer became the quiet stage that every single one of their thousands of transistors would stand on. So the real challenge was never really about proving that one tiny moly switch could work. Researchers already knew that much. The true challenge was proving that thousands of these fragile switches could work together, reliably, at the same time, without the whole system collapsing. And that is precisely the wall the Chinese research team set out to smash through. To understand exactly how they pulled it off, we need to look at what they actually built, piece by piece. From one switch to 6,000. The team behind this breakthrough is based at Fudan University in Shanghai. They spent roughly 5 years chasing this one goal. Instead of building yet another small test transistor to sit on a lab shelf, they wanted to build an entire working computer processor out of this atom-thin material. They named their creation WUJI. The finished chip packed in about 5,900 of these moly transistors, all wired together on a single piece of material roughly the size of your fingernail. To really understand how big of a leap that is, remember that the old record was just 115 transistors. This team jumped from a couple hundred all the way up to nearly 6,000 in one single project. That is not a small step forward. That is closer to a giant leap. They did not stop at building just one chip either. The team fit 24 separate chips onto a single round sapphire wafer, only about 4 inches wide, similar in size to a small coffee coaster. Cramming that many complete working processors onto one small disk meant their manufacturing process had to stay incredibly consistent across the entire surface, not just in one lucky corner. For the wiring that connected all those tiny switches together, the team even mixed 2 different metals, aluminum and gold, choosing carefully where each one went to help fine-tune exactly how each individual switch behaved. It was less like building one machine and more like tuning thousands of tiny machines to all sing the same note at once. Getting thousands of these delicate, atom-thin switches to behave exactly the same way was incredibly difficult. Even tiny, invisible differences during manufacturing could cause a single transistor to fail completely. A speck of dust smaller than you could ever see, a slightly uneven layer of material, or a tiny shift in temperature during production could throw off how one switch performed compared to its neighbor. When you are only connecting a handful of transistors together, a couple of bad ones might not matter very much. But when you are connecting thousands of them into one working system, even a small number of failures can break the entire chip. To fight this exact problem, the researchers brought in computer learning tools, similar to the kind of artificial intelligence tools used to spot patterns in huge piles of data. Think of it like running a factory assembly line, where a handful of workers keep making the exact same small mistake, but nobody can figure out why. Instead of guessing, these learning tools quietly studied every step of the manufacturing process, comparing thousands of tiny details, until they spotted the hidden patterns connecting what worked and what kept failing. Using those insights, the team fine-tuned each step of the process, over and over, until it became far more consistent than anyone had managed before. By the end, they reached an incredible success rate, with well over 99% of their transistors working exactly as intended. For a brand new, experimental material that nobody had ever built at this scale before, that level of reliability is genuinely stunning. Once they had a dependable way to build the individual switches, they still needed a way to organize thousands of them into something actually useful. A single transistor by itself cannot do math, and it cannot store information either. All it can really do is turn on or turn off. To build something as complex as a real processor, engineers combine transistors into small teams that each handle one simple job. One small team might flip a value from a 0 to a 1. Another might compare two numbers to see which is bigger. Another might hold on to a tiny piece of information so it does not get lost. Those small teams then get combined again and again, stacked on top of each other in clever ways, until you end up with something powerful enough to actually run real computer programs. The Fudan team built an entire toolbox of these small combined units, 25 different types in total, all made from scratch using their new moly transistors. That toolbox gave them everything they needed to design and build a genuine, working processor, instead of just leaving behind a messy pile of disconnected switches. For the chip's overall design, the team chose to build it around an open set of computer instructions known as RISC-V. Think of RISC-V as a shared language that computer chips can understand, kind of like how English lets people from different countries communicate with each other. Most popular computer languages like this one usually come with a hefty price tag attached, sort of like paying rent every single month just for permission to use somebody else's design. RISC-V works differently. It is free for anyone to use, sort of like owning your own house outright instead of renting one. That freedom is a big part of why so many researchers and companies around the world have started building around it. Instead of inventing a brand new, mysterious language from scratch just for this one experiment, the Fudan team used a language that engineers and programmers already understood all around the world. That choice let them test their strange new chip using real, standard computer programs to prove once and for all that it could actually add numbers, move data around, and follow instructions like a genuine, working computer processor. And it worked. The finished chip could run basic programs successfully. It could add and subtract numbers correctly. It could move information between its different internal parts, just like the processor sitting inside your phone or laptop does, quietly, every single second of every single day. Now, here comes the twist that trips a lot of people up when they first hear this story. This chip is incredibly slow. It only runs about 1,000 times every second. A modern phone or laptop processor runs billions of times every single second, without ever slowing down. In terms of raw speed, there is almost no fair comparison to make at all. This tiny moly chip could never run a modern video game. It could not load a website. It could not even handle a simple app on your phone. So why on earth does any of this actually matter? It matters because speed was never really the point of this experiment in the first place. The real point was proving that this ultra-thin material could be organized into one full working system, instead of just sitting there as a handful of separate switches on a lab bench somewhere. Think about the very first airplane ever built. It could barely fly a few hundred feet off the ground, and it definitely could not compete with a modern passenger jet in any way. But it proved, for the very first time, that powered flight was actually possible. Every single airplane that came after built directly on top of that first clumsy, unimpressive proof. This strange little chip is playing that exact same role for atom-thin computer technology. It proves the idea genuinely works at a real, usable scale, not just inside one perfect, hand-picked lab sample. That is genuinely exciting news. But before anyone gets carried away imagining these chips replacing your phone next year, we need to talk honestly about how far this technology still has to go and where it might actually end up being useful first. The catch and the big payoff. Let's be completely honest about the size of the gap that still exists here. This chip's tiny switches are still much bigger than the switches packed inside a modern silicon chip. A cutting-edge phone processor holds tens of billions of transistors, built at sizes so incredibly small that they make this new chip's switches look enormous by comparison. almost like comparing a basketball to a marble. Closing that gap will take years of extra research, brand new tools, and a huge amount of funding poured into the effort. This particular chip was also built using research lab equipment, not the kind of advanced, ultra-precise factory that builds the chip sitting inside your actual phone right now. Those factories cost billions of dollars to build, and it took decades of trial and error to perfect them. Scaling this brand new material up to that same level of precision is a massive engineering challenge all on its own, completely separate from the original science experiment. There are still plenty of unanswered questions sitting ahead of this technology too. The switches need to shrink down dramatically before they can compete with anything modern. The tiny metal connections linking each switch together need to become far more reliable, so they do not wear out or fail over time. And the whole process needs to work smoothly on a massive industrial wafer, not just a small research sample handled carefully by a team of scientists wearing gloves in a clean room. None of these problems are simple, and none of them are guaranteed to be solved quickly. A working prototype proves an idea is possible. It does not prove that idea is ready for the real world just yet. So no, this chip is not about to replace the processor inside your laptop anytime soon. But focusing only on speed misses the bigger picture of where this technology might actually shine first. Modern chip designers have been trying to stack layers of circuits directly on top of each other, sort of like building upward instead of just spreading outward, to pack even more computing power into the same tiny space. The problem is heat. Building a brand new layer of silicon on top of an existing chip usually requires extremely high temperatures, hot enough to damage or completely destroy the delicate circuits already sitting underneath. It is a bit like trying to build a second floor onto your house using a blowtorch, all while trying not to burn down the first floor in the process. This is exactly where an ultra-thin material like moly could offer a real advantage. Some early research suggests these atom-thin layers might be added using much lower temperatures than silicon requires. That means engineers could potentially build brand new layers of circuits directly on top of existing silicon chips, without damaging anything already built underneath. Imagine a future chip where powerful silicon handles all the heavy lifting, while a paper-thin layer of moly sits right on top, quietly handling sensors or extra bits of processing, all packed into an impossibly compact space. There is another promising use for this technology too. Not every device on Earth actually needs billions of transistors and blazing fast speed to be useful. A small sensor, like one that monitors temperature, movement, or even health signals inside a tiny wearable device, often just needs a small amount of simple processing, using as little power as possible to keep running for a long time. An ultra-thin, low-power chip like this one could turn out to be a perfect fit for exactly that kind of job, tucked quietly inside tiny devices we have not even invented yet. The team behind this chip is not slowing down either. Reports out of Shanghai suggest plans are already underway to build a much bigger production line, aimed at pushing this kind of atom-thin chip technology out of the university lab and closer to something resembling real manufacturing. That does not mean mass production is right around the corner. Big plans and finished factories are two very different things, and a lot can go wrong between announcing a goal and actually reaching it. But it does tell you that nobody involved in this project sees WUJI as a one-time science fair project sitting on a shelf. They see it as a first step, and they are already trying to take the second one. So where does all of this actually leave us? This chip is not fast. It is not tiny by modern standards, even though it sounds tiny when you first hear about it. And it is definitely not ready to replace the processor inside your phone anytime soon. But none of that was ever really the point of building it in the first place. The real achievement here is proving that thousands of impossibly thin switches, each one only 3 atoms deep, can actually be organized into one working, programmable system that runs real code. That single fact quietly shifts an entire field of scientific research forward. The conversation is no longer just about whether this strange, ultra-thin material can switch electricity on and off in a lab. It is now about how quickly engineers can shrink it further, strengthen it, and scale it up towards something the rest of us might actually use one day, in devices we have not even thought of yet. Every major piece of technology in history looked slow, clumsy, and completely unimpressive the very first time it worked. The earliest computers filled entire rooms and were slower than the phone in your pocket today. The first cars could barely outrun a horse. The first airplanes could barely clear a fence. This tiny, 3-atom-thick chip fits right into that same list. It is not impressive because of what it can do today. It is impressive because of what it proves is now possible. So think back to that opening question. How can something 3 atoms thick, thinner than smoke, thinner than a soap bubble, actually run computer code at all? The answer was never a magic trick. It was 5 years of careful, stubborn engineering, thousands of tiny failures quietly fixed one at a time, and a team willing to chase a nearly impossible goal until it finally worked. The only real question left now is how quickly the next few years turn this fragile lab experiment into something the rest of the world can actually hold in their hands. If this kind of story genuinely interests you, our deep dive into why every phone on Earth still runs on the exact same material is a perfect next watch, and it connects directly to everything we just covered here today. Before you go, hit that like button, subscribe if you are new here, and tap the notification bell so you never miss the next big breakthrough before it hits the mainstream news. Now I want to hear from you. Do you think these atom-thin chips will eventually take over from silicon completely, or will they stay stuck in the lab as a neat science experiment that never quite makes it out into the real world? Drop your answer in the comments below.